Hello, I'm Sanjay Tarinder from University of Moratuwa, and I will be presenting the paper Re-evaluating Keystroke Dynamics for Continuous Authentication. In this presentation, I will first give a brief introduction to our research area and problem. Then I will be presenting the purpose of the study and a small review of our literature area. Next, I will be speaking about the research process we followed. Then I will be presenting about the evaluation metrics which we used for the paper. Finally, I will provide an analysis of our obtained results. First, let me give you a brief introduction to our study. In the modern day world, there's a rapid increase in the usage of mobile devices. People increasingly rely on these devices more and more in various areas of their lives. These include banking, health, shopping, and many more. These applications store sensitive data. Also, these devices are small and easily shareable or lost. Therefore, the security concerns in smartphones are also increasing, requiring a higher level of security. The current authentication methods today, such as fingerprints, face IDs, pattern locks, and PIN codes, have major security issues. These include guessing, sniffing, social engineering attacks, shoulder surfing attacks, presentation attacks, and replay attacks, and data simulation. Being one-time authentication systems is a major reason behind these vulnerabilities. The way to overcome these issues and provide robust security is through continuous authentication, which focuses on continuously authenticating the user while using the device. Continuous authentication is achieved through behavioral biometrics. As a definition, behavioral biometrics can be described as a field of study related to the measure of uniquely identifying and measurable patterns in human activities. When we use smartphones, there are some unique traits such as typing, swiping, and scrolling. Behavioral biometrics is a field of study in uniquely identifies these measurable patterns. As I said before, behavioral biometrics is used for continuous authentication. Among the behavioral biometrics used for continuous authentication, keystroke dynamics is the most popular behavioral biometric. Now, let's look at the problem we are addressing in our study. State-of-the-art mobile continuous authentication systems have been evaluated through traditional evaluation metrics such as accuracy, precision, and F1 score. However, since these are continuous authentication systems, it is important that they are evaluated through time, but no such evaluation has been done. Therefore, the purpose of this paper is to evaluate the state-of-the-art keystroke dynamics-based continuous authentication systems through time using continuous evaluation metrics. Now, let's take a look at a brief overview of the literature survey for this paper. Behavioral biometrics-based continuous authentication systems have first been built with traditional machine learning models using algorithms such as random forest, KNN, and SVM. After the emerging of deep learning approaches, systems have been developed with deep learning approaches such as recurrent neural network and long short-term memory. The latest trend includes transformers. In our work, we are adapting three systems from those literature reviews. Those systems are named as HumanNet, TypeNet, which use LSTM models, and Typeformer, which uses a transformer-based approach. Now, let's take a look at the research process we followed for this paper. First, we identified the datasets and models to be developed. We chose AltoDB as our dataset. Next, we developed 6 models. 3 of those models included deep learning approaches, and the other 3 included traditional ML methods. Next, we evaluated all these models with a traditional evaluation metric. The metric we have chosen is EER, which is the equal error rate. EER is the location on a ROC or DET curve where the false acceptance rate and false rejection rate are equal. Next, we do our evaluation with continuous evaluation metrics. We have chosen 4 evaluation metrics, which are usability, TCR, FRWI, and FAWI. The definitions for those evaluation metrics will be covered in the coming class. Finally, we analyze all of these results. Now, let's go through the definitions of continuous evaluation metrics we've used in our study. These evaluation metrics have been used for computer continuous authentication systems, but not for mobile continuous authentication systems. First, let's look at usability. Usability is the fraction of the total time that the legitimate user is granted access to the protected resource. High usability is vital for an authentication system. Next, let's look at false reject verse interval. False reject verse interval is the longest time interval over which a legitimate user might be falsely rejected and marked as an imposter. A low FRWI is also important for better usability. Now let's look at false accept verse interval. False accept verse interval is the longest time interval over which an imposter can be falsely accepted as a legitimate user. FAWI evaluates an important security aspect, and FAWI should be minimized as much as possible. Now let's look at time to correct reject. Time to correct reject is the interval between the start of the first action taken by the imposter to the time instant that the system correctly rejects it. The TCR should also be low for better security. Now let's take a look at the analysis we can get from the results obtained. This slide includes the results of all 6 models with respect to EER. As you can see, RFC model has achieved the best results. KNN TypeNet have also achieved close results. Now let's look at usability results. As you can see, here random forest achieved the best results. KNN, GBC, and Typeformer have also achieved closer results. Now let's look at FRWI results. As you can see, RFC and KNN models achieved the best results. Kubernetes and Typeformer have also achieved close results. Now let's look at the FAWI results. As you can see, KNN, RFC, and GBC models have achieved the best results. TypeNet has also achieved somewhat closer results. Now let's look at the TCR results. As you can see, GBC achieved the best results. TypeNet has also achieved close results to best. By analyzing all these results, we observe that CA evaluation results and traditional evaluation results do not agree on a single best performing model. Rather, we see different models performing well on different evaluation metrics. The evaluation metric usability has shown the most similar performance to traditional evaluation results. While traditional evaluation metrics would have us believe that the RFC model outperforms all other approaches, looking at the CA evaluation results highlights a different perspective. While RFC offers the best usability, GBC provides a better TCR. Further, these results are not sufficient for real-world usage. For an example, the best FAWI was 0.82 minutes, which is approximately about 50 seconds. This means that an imposter user will be able to use the device for 50 seconds. This highlights the need to use these CA evaluation criteria for evaluating behavioral biometrics for the use of CA. Based on the application requirement, we can select the appropriate model to prioritize usability over security or vice versa based on this evaluation. Furthermore, for traditional evaluation metrics, an input sequence length of 70 gave the best performance in each scenario. In our study also, we observed that it is the same with continuous evaluation metrics. Here, sequence length means the time series length a model considers at a time. These slides include the references that we have used. That brings us to the end of our presentation. Thank you for your undivided attention. If you have any questions, now is the time to ask.